Hello and welcome back. This is your second lesson in calculus. We're talking about evaluating limits analytically today. We're going to learn how to take limits in 4 different ways. Number 1, by direct substitution. Number 2, by factoring or canceling. Number 3, by rationalizing the numerator. And number 4, by the squeeze theorem. Now, how should you approach a limit problem? First of all, you always try direct substitution first. I'll show you what that means in just a few minutes. Number 2, if you have a graph, use it. Remember that some limit problems are tricky, and check your one-sided limits. We talked about one-sided limits last time. 3, if you don't have a graph, evaluate the limit using algebra techniques or properties of limits. And number 4, later, in a couple chapters, we're going to learn L'Hopital's rule for limits that are in indeterminate form. Basic limits. Well-behaved limits have no trouble with direct substitution. Direct substitution is when you just plug in a number. For example, the limit as x approaches 12 of 3. We're talking about the line y equals 3. So there it is, I've graphed it for you. And the limit as x approaches 12. Well, let's look at both sides. As we approach the x value of 12 from the left, where is the graph? It's up here at 3. As we approach the x value of 12 from the right, where's the graph? It's up here at 3. The graph is always at 3. It's the line y equals 3. So the limit as x approaches 12 of 3 is 3. What about the limit as x approaches 7 of x? Again, we're talking about the line y equals x. So there's the line. As we approach the x value of 7 from the left, and as we approach the x value of 7 from the right, we're getting closer and closer to 7. In other words, take 7, plug it in for x. Okay, so the limit as x approaches 7 of x is 7. What about the limit as x approaches 2 of x to the 6th? Now I can graph it for you. This is what that looks like. As x approaches 2, we can kind of see like where it's going, but it's way the heck off the graph. So we're just going to take 2 and direct substitute it. We're just going to plug in 2. So we've got 2 to the 6th, which is 64. Now, of course, they don't stay this simple. Limit problems get more complicated. Let's talk about the properties of limits. We're going to set this up here and say that b and c are real numbers, n is a positive integer, and f and g are functions with the following limits. The limit as x approaches c of f of x is L, okay? The limit as x approaches c of g of x is K. So they're approaching the same constant, but they're different graphs. The graph of f is going to L, the graph of g is going to K. With that in mind, we know that all of these limit properties exist. It looks scary, but it's really not that bad. Number 1 is a scalar multiple. So if you take a function and multiply it by some constant, you can actually just take the limit and multiply it by the same constant. If you have 2 functions that are being added together, then their limits also can just be added together. If you have 2 functions that are being multiplied together, their limits can also be multiplied together. See where this is going? 2 functions that are being divided, their limits can also be divided as long as the limit on the bottom is not 0. You can take a function to a power and its limit to the power. This last one's a little bit trickier, but basically you're going to take the limit and apply it to the inside function. then you get a number and it's just f of that number. With those in mind, let's do a few examples. I'm going to show you this problem two ways, the long way and the short way. Long way first. The limit as x approaches 2 of the quantity 4x squared plus 3. I have two functions here that are being added together. So I can take the limit as x approaches 2 of each of them. Now when I separate them, 4x squared is first, and that 4 is actually a scalar multiple. So we're talking about this first property here. So the 4 can actually just come out. So now I have 4 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. You can take that 2, plug it right in. 4 times 2 squared plus 3 is 19. That's the long way. Now the short way is to take 2 and plug it in for x. 4 times 2 squared is 3. That's direct substitution. But I wanted to show you how limit properties work. The direct substitution property is valid for all polynomials and rational functions as long as you have a non-zero denominator. So plugging and chugging should always be your first approach. Let's try this one. The limit as x approaches 1 of this rational function here, x squared plus x plus 2 over x plus 1. First thing to do is make sure that at our limit location 1, the bottom does not equal 0. So if I plug in a 1 to the bottom, I get, let's see, 1 plus 1 is 2. Okay, so that's non-zero. Now I'll just use direct substitution through the whole thing. 1 squared plus 1 plus 2 over 1 plus 1 is 2. If you get a limit problem involving a radical, basically all you need to know is if n is odd, then you can just use direct substitution, because you can take the nth root of a negative number if n is odd. If n is even, whatever is under the radical has to be a positive number. Transcendental functions, your sines and cosines, your natural log, your exponential functions, those can also use direct substitution. Now, what if the denominator is 0? So you see this problem, and the first thing you try is direct substitution. So if you plug in 0 to the top, you get 0. If you plug in 0 to the bottom, you also get 0. So you've got this 0 over 0 thing going. That's a direct substitution fail. This is called indeterminate form because you can't, from this form alone, determine the limit. One approach then is to look for a common factor. So I'm going to factor the top of that into x plus 3, x minus 2. Now, see that x plus 3? I can cancel that out. And I have a new limit problem. The limit as x approaches negative 3 of x minus 2. And I'll just take that negative 3 and plug it in for x, and I get negative 5. But keeping track of the fact that x cannot equal negative 3. And if you graph that, see there's a hole right there at negative 3. But looking from the left and looking from the right, the graph is approaching negative 5. Okay, this one might freak you out a bit. First thing we do, of course, is try direct substitution. So you plug in a 0, you have a 0 on the bottom, and if you plug in 0, you get a 0 on the top also. So we have some indeterminate form. We can't factor the top or the bottom to help us. So what we're going to try is called rationalizing the numerator. This is one of those moments in calculus when your Algebra 2 skills are going to be very important. If you feel comfortable with your Algebra 2, then just enjoy the math and focus on the calculus. If your Algebra 2 skills are a bit rusty, Don't worry, but please make sure you understand each step before you move on to the next one. Pause the video if you need to. In calculus, your Algebra 2 skills are just assumed, and so we have to make sure that they're strong. Rationalizing the numerator. If we put some parentheses here, it might make it a little bit easier to see what we're doing. If you take radical x plus 1 and multiply it by another radical x plus 1, you're left with just the x plus 1, no radical involved. Then the minus and the plus 1's kind of cancel out the next step, and then -1 times 1 is -1. So we've gotten rid of the radical on the top. If we clean this up a bit, this is what we have. Now these x's can cancel. And now we have a new limit problem. Can we try direct substitution now? Well, if we just plug in a 0 for x, you get 1 over 1 plus 1, which is 1/2. So here's the graph of it. And you can see that as the graph approaches 0 from the left and from the right, the value of the graph approaches 1/2. It doesn't actually exist there, but that's where it's headed. The last option we have for evaluating a limit is called the squeeze theorem. Certain oscillating functions are considered discontinuous or undefined at the point of oscillation. So we're not able to determine the limit of such functions. However, we can squeeze the oscillating curve between two other known functions whose limits are known and easy to compute. In other words, the squeeze theorem is a proof that shows the value of a limit by smooshing, it's a very technical term, smooshing a tricky function between two equal and known values. There are 3 very special limits that you can prove using the squeeze theorem. The limit as x approaches 0 of sine of x over x equals 1. The limit as x approaches 0 of 1 minus cosine x over x equals 0. And the limit as x approaches 0 of 1 plus x to the 1 over x equals e. So you're going to need to memorize these, especially the first 2. So I would like to introduce you to a friend of mine. This is Jim. And when you see Jim, your job is to put your pencil down. Don't take notes. Just watch and enjoy the math. Because sometimes as you are taking notes, you can kind of miss the bigger picture of what we're trying to explain. So just sit back and enjoy the math. What we're going to do now is prove this special limit. The limit as x approaches 0 of sine of x over x equals 1. We're going to start with the unit circle. And on the unit circle, I can create a triangle. I'm going to have a theta here, an angle of x. This is the unit circle, so it has a radius of 1. And I know that the coordinates of this point on the unit circle are cosine x and sine x. So the height of that triangle is sine of x. Now, if I expand that triangle, okay, and now I make the bottom edge of the triangle 1, I know that the first coordinate is 1, but what's the second coordinate? Okay, the second coordinate is actually tangent of x. Now, where the heck did that come from? The tangent of x is opposite over adjacent. I know that from the perspective of x in this green triangle, my adjacent side is 1. So I have opposite. It looks like a 0, so I wanted to make sure you know that that's opposite. Opposite over 1. Well, that means that the tangent of x equals the opposite side. So the opposite side is the tangent of x. Crazy, isn't it? All right, moving on. We have this arc here created in the middle of these two triangles. And if you remember from geometry, the measure of an intercepted arc of a central angle, that's the angle starting in the center of the circle, the measure of the intercepted arc is the same as the measure of the angle itself. So you can see here, I've got sine of x, and then I've got the intercepted arc, and then I have the tangent of x. X is smack in the middle. Now we're going to do some magic. Everything I do is legit, but you may not think about doing this on your own. First thing I'm going to do is make tangent into sine over cosine, okay? Then I'm going to take the reciprocal of all of them, flip everything upside down. Next, what I want to do is, I got to get rid of these sine of x on the bottom, so I'll multiply everything by sine of x. Okay, where are we going now? I've got 1 less than or equal to the sine of x over x. Ooh, look at, we're getting close to what we need, is less than or equal to the cosine of x. Now, if I take the limit of each of those, I know the limit as x approaches 0 of 1 is 1. Using direct substitution, I know that the cosine of 0 is also 1. So this guy gets squeezed in between 1 and 1. Therefore, the limit as x approaches 0 equals 1. And there it is graphically for you to see. Isn't that cool? Again, you don't have to know how to do that. I want you to see the magic behind the math. Okay, using these 3 special limits, let's do a couple problems together. The limit as x approaches 0 of tangent x over x, that doesn't match any of those. But if I can manipulate it a little bit, I might be able to find one of these special limits hiding inside of our problem. So the first thing I'm going to do is just separate those 2 functions. So I've got tangent of x times 1 over x, and then tangent of x I can rewrite as sine over cosine. I'm getting closer here. Look, sine of x over x. If I can just rewrite this a little bit, now I see something that I know. The limit as x approaches 0 of sine of x over x is 1. And then the limit as x approaches 0 of 1 over cosine 0 is also 1. All right, let's just put it all together with some practice. So first thing we have is the limit as x approaches 5 of negative x squared plus 5x. First thing you do is try to just plug in 5, and that works just fine. We get 0. This one's a little bit trickier because if you plug in negative 2, you get a 0 on the bottom. So let's try factoring the top to see if there's something we can cancel. And there is. So once you cancel it, now you can try direct substitution again. So we have the limit of negative 5. If you see a radical, you might want to consider rationalizing the numerator. So you multiply the top and the bottom by the conjugate. So instead of a negative 2, we're multiplying the top and the bottom by that plus 2. Then use your amazing algebra skills to simplify this. You can combine some like terms, negative 3 minus 4. Now that becomes x minus 7, which is really close to 7 minus x, but not quite. So if I pull out a negative from the 7 minus x, I can actually switch those to that, okay? So we are here. Now we can cross out those x minus 7s. We have a new limit problem. Now just plug in 7 and the answer is negative 1/4. Okay, this one's kind of cool. I like the way this one works out. The limit as x approaches 0 of sine of 5x over x. Now it almost matches this one, but not quite because of this silly 5 here. So I'm going to do some math magic. I'm going to multiply the top and the bottom by 5. So I have a new limit problem, and I'm going to take that 5 and as a scalar multiple, pull it out to the front. And now I have this new limit problem. The key to this special limit here is that as long as those two match, the special limit is in play. So I've got 5 times my special limit here, which is 1. Okay, last one. This one looks terrible, doesn't it? The limit as x approaches the natural log of 2, yuck. If we plug in the natural log of 2, we end up getting a 0 on the bottom, so that's not going to work. But what you're supposed to recognize on this is e to the 2x minus 4 is actually a difference of squares, so we can factor the top into 7 times e to the x plus 2 times e to the x minus 2. Now I've got that e to the x minus 2 that I can cancel, and now we can do our direct substitution. E to the ln 2, that's going to become the same thing as 2. So we've got a final answer there of 28. That was a lot, y'all. That was a lot. But thank you for hanging in there with me, and I'll see you next time.